All right, so it looks like it is time to start. So, hello everyone. I'd like to introduce today's lecture for the Nuclear Engineering Summer School. Today we'll be having Dr. Andrew Wilhelm be talking about some of his dissertation work on opaque scintillators. As a reminder, similar to how we've been doing this week, feel free to ask any questions in the Q&A panel, and we'll be holding a question and answer session at the end of this lecture. Cool. So without further ado, go ahead, Andrew. The floor is yours.
All right, thanks, Ricardo. Um, as he said, my name is Major Andrew Wilhelm. I'm a recent graduate of the University of Michigan, and now I'm on the faculty at the Military Academy at West Point, doing a temporary duty assignment down at Army Futures Command. So if anybody has any questions about that, please feel free to shoot me an email at the link below. I always feel the need to do a little soft recruiting, um, when I have engagements like this. So would love to chat with you about any of those topics if you're interested. But today I'm mostly going to be talking about opaque scintillators for radiation detection, which, as Ricardo mentioned, was the topic of my thesis. Um, so without further ado, the agenda for today, I'm going to introduce scintillators and sort of what we mean when we say event topology and why we care about it. I'm going to talk about how opaque scintillators work and how they differ from conventional or traditional transparent scintillators. Some work that we did in the theory and modeling of light transport in opaque scintillators, and then I'll move into a description of some prototypes that we put together based on two different scintillation liquids. And then I'll discuss sort of the performance of those prototypes as they pertain to the reconstruction of event topology for point-like events. And then I'll conclude with a look at sort of what the future holds for opaque scintillators. As Ricardo said, please feel free to pop any questions into the chat as they arise, and we can talk about them as they come up, or at the end if you'd prefer. Okay, so scintillators and event topology. First of all, what do we mean when we say event topology? So event topology is information about when, where, and how much energy is deposited in a detector during an event. So you can kind of think about this as the spatial and temporal distribution of light creation inside a detector volume. So here in the image above, if we had perfect information about the event topology, we would know exactly how much light was created in each of those three locations and exactly when it was created and how much was created. And there's a lot that we can do with that information. So traditional scintillators, and when I talk about scintillators, I know that there's a vast array of possible designs, but I mostly mean the ones that we see in sort of normal radiation detection laboratories. So they're usually small crystals or small cell liquid organics, as you see in the image here on the right. And there are many salutary characteristics of these type of scintillators. The light collection is very efficient, which means that for an amount of energy deposited, generally you receive an amount of light that's proportional to that, which results in good energy resolution. They're simple, they're inexpensive, and they're useful in a variety of scenarios. So here on the left, you have sort of just a simple schematic of a traditional scintillator. A gamma ray is incident onto the volume, deposits some energy after an interaction, and that results in the creation of photons of visible light. So in a traditional transparent scintillator, we want to collect all of those photons at some boundary at a photosensor. So in order to do that, we want this volume to be reflective on the inside and as transparent as possible, such that all of the light, or as close to all the light as we can arrange, makes it to this photosensor and is collected. And we want that to be true regardless of whether this event occurs near the center of the detector or near an edge. So as a result of that and that efficient collection, we don't natively have any information about where this event took place, because we're going to see a similar signal at the photosensor kind of regardless of where this event occurred in the detector volume. So the only drawback really of a design like this is that you don't natively have information about event topology. So why do we care about event topology? Well, there are a variety of reasons. I'm going to highlight three here. So the first one is in a traditional scintillator, if you have two events occur at the same time, be it from two different particles or a single particle interacting multiple times within a short time window, what you'll see at your photosensor is just a burst of light that is representative of the sum of energy deposition between these two events. So you won't be able necessarily to tell that there were multiple events, or if you can, how much light was created in each one, or where they were. So if you knew that some light was deposited here and some light was deposited here, that would indicate to you that this was a piled up event from either two particles that were incident at the same time or a single particle interacting multiple times. So this sort of telltale sign of pileup can be understood with event topological information. Another reason, and I know you've had some talks on imaging so far this week. So imaging is something that requires knowledge of event topology. So in sort of the canonical Compton camera application, you have an incident gamma ray that scatters at some location and then is absorbed via the photoelectric effect at another location. And if you have full knowledge of where those events took place, as well as how much energy was deposited in each event, you can use that information to calculate a cone that points back towards the source. So this is sort of another application of why we might be interested in knowing event topology. And then a third is particle type identification. So when I'm talking about particle type identification, I don't necessarily mean between gamma rays and neutrons, because both of those interactions in a scintillator are point-like. But some particles interact in a very characteristic fashion and deposit energy in a very characteristic way inside a scintillation volume. So here in the upper left, you have a schematic that shows a muon from a cosmic ray depositing energy kind of along a long track all the way through a detector. And that's because they're highly energetic and highly penetrating, and are also charged particles. And so they're going to deposit energy all along their track, usually penetrating all the way through a detector. So if you had information about where this energy was deposited, it would be very clear that it was a track-like event, and that would tell you, potentially what kind of particle it was. Conversely, if you're looking for a rare event, something like an antineutrino-induced inverse beta decay, sometimes there's very characteristic interaction patterns that can help you identify that it was that type of particle that interacted. So here we have an antineutrino that interacts with a proton, and it results in a energetic positron and a fast neutron. So the positron is going to deposit energy locally since it's a charged particle, resulting in a flash of light right there. And then it's going to annihilate since it's antimatter, resulting in two anti-parallel 511 keV gamma rays. And so you're going to end up with a flash of light here and here. And those three flashes of light are going to be all along the same line. While that's occurring, or actually after that's occurring, this fast neutron is going to scatter throughout the volume, depositing its energy all along its track, and then eventually be absorbed if there's something in the scintillation compound that absorbs thermal neutrons. And so at some later time, at some different location in the detector, you're going to receive another flash of light. So this thumbprint is very characteristic of this rare event. And if you have good knowledge of the topology, you can use it to feel confident that is in fact the interaction that you're observing. So again, none of this would be possible if you're just using a single photosensor with sort of a traditional scintillator design. So there are ways of getting event topology from transparent scintillators. There are several. I've highlighted a couple here, but this isn't meant to be a comprehensive list. So one of the ways is by using timing information. So here in the upper left, you can see a plastic slab scintillation detector. And so if you imagine you have an event occurring at this location here, then the time it takes for light from that event to reach this photosensor will be shorter than the time it takes for this light from this event to reach this much further away photosensor down here. So by comparing the different timestamps of light arrival at T2 and T4, that gives you an indication of where that event took place. And then similarly, between T3 and T1, that gives you sort of the other dimension. So this allows you to reconstruct in 2 dimensions the location of an event in a detector of this type. It does require quite good timing, or I should say the position resolution is related to how precisely you know the time of arrival of those photons. Another way of doing this is by physically segmenting a detector or having a detector array. So down here in the bottom left, you can see an array of detectors. This is meant to be a dual particle imager. So you can imagine if you have an interaction in this detector here with a gamma ray, which then goes on to be absorbed in this detector over here, then you know both the position as well as the energy deposition for those two events because you know the locations of those detectors. And you're able to do the Compton imaging that we described earlier. So the downsides of an approach like this are that it's difficult to instrument, a large fraction of the experimental volume. So you're sort of choosing different spots to instrument, and then also the resolution of the system is limited by the size of the detector. So the larger the detectors are, the more uncertainty you have in the position of interaction. And then lastly, on the right, is an image of the sand detector, which is sort of a combination of these two ideas. So in the XY plane, you have physical segmentation. So it's similar to the detector array at the bottom, where you have sort of bars of scintillator. And if an interaction takes place in one of those bars, the light is confined to that bar. So once again, the position resolution is limited by the size of the bars. The larger they are, the worse the position resolution. And then in the Z direction, they're using relative timing between the photosensors at the top and the bottom to get a Z coordinate similar to what I described in the upper left here. So those are some of the ways that we measure event topology. There are benefits and drawbacks to each of these designs. Okay, so now that we understand how traditional scintillators achieve event topological reconstruction, I'm going to start describing opaque scintillators and how they're different and kind of what their operating concept is. Okay, so once again, here in the upper left, we have a traditional transparent scintillator with the photosensor at a boundary. We have an incident gamma ray that scatters 2 times and then escapes, and all the light that is generated from that event is collected efficiently at that photosensor. Conversely, in an opaque scintillator, we intentionally design the medium to be highly scattering. So I want to emphasize that we still don't want the light to be absorbed. We want the scintillation liquid to have as long of an absorption length as we can manage, but we want it to have a very short scattering length. So if you imagine for a second that you are a photon and you're born in this location here from this interaction event, you're only going to be able to travel a short distance before you're scattered in a random direction. And then you'll travel another short distance, be scattered in a random direction again and again and again, such that over time, while you still have a long total path length, your displacement is small, or the distance that you travel away from your origin is small. So another way of thinking about it is both of these lines down here have the same total length, meaning the path length of the photon travels the same distance before it's absorbed. But clearly down here, because this path is folded up on itself due to repeated scattering, that photon can't make it very far away from where it originated. And we call this effect stochastic light confinement. So it sort of achieves the same thing of a segmented detector, a physically segmented detector, without the need to physically segment the detector. So a problem of this design is that unlike the transparent scintillator on the left, where we can put a photosensor at a boundary and efficiently collect the light, if we try to do that in an opaque scintillator, we won't see any light at all. So none of this light will make it to this boundary because it's stochastically confined. So in order to get the light out, we have to introduce wavelength shifting fibers into the medium. And I'll explain more about how wavelength shifting fibers work here in a minute. But for the time being, you can just think of them as being a way for the light to kind of escape this scattering medium in which it is created. So if we interlace a bunch of wavelength shifting fibers in a volume like this, it allows us to create sort of an image of the light balls that were created inside the detector. So now we're looking sort of from the top at this opaque scintillator with this lattice of fibers, and you can see that we're collecting light, from this event in these 4 fibers, and the fact that the amount of light that was collected in each of these fibers is similar tells us that event probably took place close to the center of that cluster of 4 fibers. And then down here, this second light ball, we're collecting a lot of light in this central fiber, a little bit less light here and a little bit less light here. And that allows us to sort of hone in on where that event took place. Um, Another thing to notice is that if we have fibers going in one direction in a detector like this, it provides us with a two-dimensional image or a two-dimensional position reconstruction capability. And so if we want to be able to reconstruct in 3 dimensions, we have to introduce another set of fibers that is orthogonal to this first set. Okay, so wavelength shifting fibers, how do they work? So here's some pictures of them up here on the top. So you can see if you're looking at a wavelength shifting fiber, which is just it's like a thin plastic, flexible optical fiber. These are 1 millimeter in diameter. They sort of have this glow, almost as though it's powered in some way. But what's happening is it's collecting light from its environment through the sides of the fiber and kind of redirecting it down the length of the fiber. So it sort of has a light concentration effect. So a lot of people, when they first see a wavelength shifting fiber, assume that what's happening is light is incident on the fiber, and just due to its angle of incidence, ends up trapped in the fiber and directed towards the end. And that's actually not what happens. What happens is light is incident on the fiber, makes it into the core, which has a wavelength shifting die in it. That light is absorbed and then emitted at a longer wavelength. Sometimes when it's emitted at that longer wavelength, it's emitted in a direction that is conducive for total internal reflection. And then the light is trapped and it's going to continue moving down the fiber until it reaches the end. So this is what we want to have happen in a detector of this style. Unfortunately, what usually happens is light is incident on the fiber, it's absorbed on the interior of the fiber, and then it is re-emitted in a direction that is not conducive to total internal reflection. So it just escapes. And that's why when we look at these fibers, when we're looking at the sides of them, they don't appear dark. A lot of light is being emitted, a lot of green light is being emitted from those fibers, which is why we're able to see them the way that we do, why they appear green. So these are not perfectly efficient, and I'll talk more about that in a second, but a lot of light is lost kind of out of the sides of these detectors. But you can see, they are successful in delivering light to the end as well. Okay, so the chain of detection in an opaque scintillating detector is important to understand because there are many steps, and kind of each one introduces a little bit of inefficiency. And so I'm going to kind of walk through all the steps of how a photon ends up being detected in an opaque scintillator based on what we've just discussed. And I'll just provide sort of like a ballpark estimation for the inefficiency of that step. And you can see why this is sort of a challenging thing to do. So the first thing that has to occur is an incident particle has to interact in the volume, obviously. It has to deposit energy in some way and create light. So then we have a scintillation photon that has been produced. And in order to detect it, the first thing that has to happen is that scintillation photon has to make it to a fiber before it's either absorbed in the bulk medium or escapes out of the sides of the detector. So in a well-designed detector where the fiber spacing and the optical properties are appropriate and well thought through, you can expect about 70% of photons to make it to a fiber and be absorbed inside a fiber. Once they're absorbed in a fiber, about 80% of them are going to be re-emitted at a longer wavelength. It's not a completely lossless process, but it's fairly efficient in that step. So now we have a wavelength shifted photon that has been created inside the core of a fiber. So this is the most lossy step where we ask the question, what fraction of those photons that are emitted inside the fiber are going to undergo total internal reflection and stay in the fiber? And the answer to that is it's about 10%. So we lose 90% of the photons that are absorbed and re-emitted in the fiber out of the sides. And about 10% of them are emitted in a direction that is, allows them to be delivered to the end of the fiber. About 90% of those will actually reach the end of the fiber without being absorbed or sort of rescattered and escaping the fiber. So that, again, that's like a fairly efficient step. And then lastly, once the photon makes it to the end of the fiber, it then has to be detected by a photosensor, for instance, a photomultiplier tube or a silicon photomultiplier. And there I've used as a benchmark about 25%, which is sort of a typical quantum efficiency for a photomultiplier tube. So if you multiply all those probabilities together, you'll see that usually less than 1% of the photons that are created in the volume are going to be actually detected in a detector of this style. So the Liquid O collaboration, which is a group that studies this, has a saying that every photon is precious. We have to be as careful as we can with every photon because it's such a lossy process that in order to to build a detector of this style, you have to be very careful that you don't introduce further losses into the detection chain. Okay, so now I'm going to move into some experimental work that I did at the University of Michigan as part of my graduate studies. So the first thing I'm going to discuss is our efforts to kind of understand the light transport and the light collection in a detector of this style, and some modeling that we did to help us understand those processes. So the first thing that we wanted to understand is what factors determine the light collection efficiency from opaque liquids into the fibers. And in order to do this, we wanted to remove the complexity of scintillation mechanisms, and we wanted to use an inert opaque liquid. So we actually ended up using diluted cow's milk as a highly scattering but optically inert liquid. And then the origin of the light was actually a pulsed laser that was coupled to a fiber optic cable. And this allowed us to inject a known number of photons at a known location into a volume. And then we could measure the response of each of these fibers to that known impulse that we could control. The whole thing was housed inside a dark box, and the wavelength shifting fibers terminated at a multi-anode PMT, so we could read out each of the fibers individually. So the first experiment that we investigated was we wanted to see if our intuition was correct, and that if you have more scattering in a liquid, the light will be more efficiently collected for events that take place very close to a fiber. So said another way, if we inject light really close to a fiber and there's not a lot of scattering, we would expect that light to move away from that fiber and kind of escape and not be efficiently collected. But if we inject light really close to a fiber into a highly scattering medium, we expect that light to be confined in a region close to the fiber, such that it can be efficiently collected. And so we would expect there to be a positive relationship between more scattering and better collection. And so that's what this plot shows here on the left. Moving from left to right on the x-axis, we're increasing in milk volume fraction. So we're sort of increasing the amount of scattering in this liquid. And then on the y-axis is photoelectrons per pulse. And you can see that as the liquid becomes more and more scattering, we're collecting more and more of those photons. Interestingly, it seemed to be reaching some sort of plateau here, and I think that indicates that up here we're efficiently collecting most of the photons. So if we continue to shorten the scattering length of this medium, we won't continue to see additional gains, and that's reflected in our estimation of most of the photons are collected into a fiber in a system of this type. So next, we wanted to know how the light collection efficiency in a system like this depends on distance from the event. So we built this sort of lattice of fibers that allowed us to measure the amount of light that makes it into a fiber as a function of distance from the center. So once again, we were injecting light into the center using our fiber coupled laser, and then we could measure at various distances the light collection efficiency. So here is a plot showing the results of that experiment. In the upper left, this first data point, those are the fibers that are closest to the center. And you can see that the effect is similar to the plot that we looked at before, which is that as you increase the milk loading in our inert opaque liquid, and thus increase the scattering, you get more and more light into that nearest set of fibers. Interestingly, and what's good for a detector of this style is that not only do you get more and more light in the fibers that are close to the event, but also the amount of light that is collected at fibers far away from the event is suppressed as you increase scattering. So for fibers that were far away from an event, when there's a small amount of scattering or there's a long scattering length in the material, a lot of light is still collected at these distant fibers. But as you increase the milk loading and sort of shorten the scattering length of the liquid, the amount of light that is collected at these distant fibers is suppressed. And that is positive for us to be able to have a good understanding of where that event took place. We want all the light to be localized close to where it was created, so that we can feel very confident about where the events were. That's kind of the whole purpose of what we're doing. Okay, so from there, once we had a good understanding of sort of the way that light was collected in these fibers, we moved on to prototype design. We had a few objectives with our initial prototypes. First, we wanted to compare the two major categories of opaque liquids that are under consideration. Sort of the two families are wax-based and emulsion-based opaque scintillation liquids. So wax-based, I'll give you examples of both of them here in a minute, but essentially one of them it has a temperature dependency because it has paraffin wax in it. And then the other one is sort of like a liquid and water, or sorry, an oil and water suspension. We wanted to be able to measure the energy resolution, and we wanted to be able to measure the topological reconstructive power. Our constraints in our design were that we were limited to 32 channels of instrumentation. We wanted to be able to do a three-dimensional topological reconstruction, and so that required the use of fibers running in orthogonal directions, as we discussed earlier. And then it unfortunately needed to be feasible for a range of optical parameters, meaning we didn't know exactly what the characteristics of the liquids we were going to receive were. And so this design had to sort of accommodate a variety of scattering and absorption lengths rather than be optimized for one set. Okay, so this is an image of our first prototype, which was made from welded aluminum. The dimensions of the cube are 10 centimeters on a side, so it's a 1 liter volume detector, so fairly small. It has, as I mentioned, 32 wavelength shifting fibers in orthogonal directions, sort of interleaved in 8 layers of 4 fibers apiece. Those fibers terminate in a 3D printed multi-anode PMT interface to hold the fiber ends onto the multi-anode PMT and allow us to read out each of the channels individually. So this is a sort of a description of what it was like to make the wax-based opaque liquid, which is called No Wash 20. There's a good paper on that that I have a reference for at the end. It was developed in Germany initially. And it's pretty simple what it is. Really, it's 80% linear alkyl benzene, which is just a solvent, and 20% paraffin wax, which is why it's called No Wash 20. So you heat up the linear alkyl benzene to about 60 degrees Celsius, add in the paraffin wax until it melts. And when it is at an elevated temperature, it's very transparent, as you can see down here. So here's us adding a wavelength shifter, POPOP, in order to make the color of the light appropriate for the fibers we were using. But you can see after that dissolves, this is with the paraffin already added. It's highly transparent and easy to pour and work with at these elevated temperatures. So then we poured it into our cube and allowed it to cool to room temperature. And here you can see some images of the liquid cooling. As it cools, it starts to develop a skin on top, because it's cooling from the outside in. So that cools first, and you can see the start of that crystallization as the liquid becomes opaque. And then by the time it reaches room temperature, fully opaque, you can no longer see the fibers inside. And due to a contraction, a lessening of the density, you do have this effect of volume collapse, which we were able to mitigate somewhat in later iterations by reducing the temperature at which we poured it. But this is, just sort of an engineering consideration for if you're going to use a wax-based liquid scintillator, you should expect it to change in density as it cools. So here's some images of under UV elimination, what the detector looked like at 2 different temperatures. So the first one is 33 degrees Celsius. So that's kind of in between these top 2 right images here. And then at room temperature on the right. So when we illuminate with UV, you're able to make out easily all the fibers all the way to the bottom, indicating that liquid is still transparent to the scintillation light, or to the wavelength shifted light, I should say. But once it cools, it becomes fully opaque, and we can just kind of make out that first row of fibers, and the rest of the light is being confined inside by that short scattering length. So next, we exposed our prototype to gamma rays from 2 radioisotopes, cesium-137 and cobalt-60. So cesium-137 has gamma rays of about 660 keV, and the gamma rays from cobalt-60 are about twice as energetic, which is why when you compare sort of the blue circles and squares here, you can see that the squares indicating the gamma rays from cobalt-60, the more energetic gamma rays, result in sort of more signal per interaction. And that's because they're creating more light because those gamma rays are depositing more energy. So this showed us that our detector could distinguish between different radioisotopes, and it had a different response for gamma rays of different energies. Notably absent from this is any sort of which is what you'd expect in an organic scintillator of the type that I showed at the beginning. So the response is quite smeared out, and there's a couple reasons for that. One of them is that the light collection is just not very efficient, and so the features are lost because of that. And then additionally, we have this added dependency on position. So the light collection is like a little bit different depending on where in the detector the event occurs, and that also smears out the features. The other thing to take away from this plot is that the addition of POPOP, which we did in our second generation prototype, greatly increased the signal collection. And that was because the emission spectrum of the scintillation liquid was more appropriate to the fibers we were using. So if you're going to design a detector of this type, it's very important to spend time thinking through what the emission spectrum of the scintillator is and the absorption spectrum of the fibers and making sure that they're well matched. Okay, so next we developed a prototype using what I'm calling emulsion-based liquid scintillator, which is in this case, a water-based liquid scintillator. So this was developed at Brookhaven National Lab. They've been working on it for about 15 years. And initially, all of the water-based liquid scintillator that they developed was highly transparent. So an absorption length of, tens of meters and a scattering length of, on the same order of magnitude. They were developing these scintillators for large anti-neutrino detection experiments where you want the amount of scintillation light to be approximately the same as the amount of Cherenkov light you get. So they were intentionally diluting the scintillator to reduce the light yield of the scintillator. We obviously want the opposite of all of that. We want short scattering length, and we want as high a light yield as we can get. And so they were able to design what they're calling opaque water-based liquid scintillator that has a very high fraction of scintillator compound and a low loading of water. And as a result is highly transparent, or excuse me, highly scattering. So they sent us 3 formulations of opaque water-based liquid scintillator, which we called 1, 2, and 3 based on when we received them. 1 you can see is fairly transparent, not highly scattering. 2 is actually the most highly scattering, as I'll show in a later plot, and then 3 is kind of an intermediate case. And then as a basis of comparison, here's No Wash 20 here on the right. So here's our next generation prototype, which is made of 3D printed acrylic to be compatible with the opaque water-based liquid scintillator. But the rest of the apparatus we used was the same. So the first thing we did was try to quantify the light confinement. So to understand this plot, along the x-axis, you have the summed pulse integral, which is sort of the total amount of light collected across all the fibers in an event. And these are for gamma rays from cobalt-60. And then on the y-axis here, you have the number of channels triggered. So the right way to think about this is if you had a detector with a very, very short scattering length, such that you were only ever going to collect light into one fiber, regardless of how many photons were produced, then you would have just a flat line down here at the bottom, where the summed pulse integral bore no relationship to the number of channels triggered because all that light was just so confined. Conversely, if you had a transparent scintillator, then you would expect there to be a roughly linearly proportional relationship between the summed pulse integral and the number of channels triggered, because the light can kind of go anywhere in the detector. So how vertical this line is sort of how transparent the scintillation liquid is, and how horizontal it is sort of gives you an indication of how scattering the liquid is. So once again, here in black, you have opaque water-based liquid scintillator 1, which is fairly transparent, has a relatively long scattering length, and we see that pretty sharp relationship between number of channels triggered and summed pulse integral. And then on the other end of the spectrum, down here in blue, you have opaque water-based liquid scintillator 2, in which the relationship between the summed pulse integral and the number of channels triggered is And so from that, we concluded that the scattering length of opaque water-based liquid simulator 2 was likely the shortest of the three formulations we had. Next, we compared the spectra from the gamma rays of three radioisotopes for each of the opaque water-based liquid simulators, as well as for NOWASH 20. So up in the upper left, you have opaque water-based liquid simulator 1. And the gamma rays from these, I guess, require a little explanation. So first, cesium-137, as I mentioned, has a gamma ray of about 660 keV. And then the gamma rays from cobalt-60 are approximately twice that amount of energy. And then sodium-22 here in red actually has two gamma rays, one of which is an energy that is close to cesium-137. So that's what this hump kind of looks like, the black points. And then it has another gamma ray that's 1274 keV that is similar in energy to the cobalt-60 gamma rays. And so that is this part of the curve out here. So we have sodium-22 you can kind of think of as almost like a combination of those two. So then we wanted to compare the performance of all of the scintillators to the same gamma rays. So we use cobalt-60, and you can see that the amount of signal that we're collecting for the gamma rays detected in OWBLS2 provide the largest signal. So that was the scintillation compound that we selected for further characterization. So next, we wanted to develop a model in Geont4 that allowed us to make simulated data sets for machine learning training for event topological reconstruction. In order to do that, we had to have a good understanding of what the scattering length and the absorption length of the liquids were. The direct measurement of those properties is not trivial, and we're currently working on a technique that I'll show on the next slide on how to do that. But initially what we did is we used a genetic algorithm as well as a simulation to try a bunch of different parameters and see what provided the best fit to experimental data. So here we are injecting light into the center of the detector. This plot here shows the number of photoelectrons for each of the channels. So the four channels that are closest to this fiber tip are this one, this one, this one, and maybe this one. And then we replicated that in simulation and tuned these parameters until we found a good fit. And the parameters that had the best fit were 5.7 millimeter scattering length and about a 17 centimeter absorption length for opaque WBLS2. So I mentioned that we're working on a technique to directly measure those properties. And so here's sort of an image of our attempts to do that. What you're looking at is simulated data of the surface of an opaque liquid that has been illuminated by a laser right at the center, a laser pulse. So you can see that the two plots on the bottom here have an absorption length of 0.2 meters. And the signal decays relatively quickly for those two. Conversely, on top, the absorption length is longer and the signal is decaying more slowly. So that light is sticking around for longer, and that's indicative of a longer absorption length. And then you can see that the rate of growth of these two light balls is similar to each other. And that's because they both have the same scattering length of 1 millimeter. And over here, the rate of growth of those is similar to one another because they both have the same scattering length of 5 millimeters. So this kind of gives us two uncorrelated things to see in an experiment of this, where the absorption length and the scattering length will affect the experiment differently and can be separated and sort of measured separately. So just to show that on plots, this is what the rate of RMS drift, which is sort of a measure of how fast the light balls are expanding, looks like. So you can see that the red and the blue lines are very close to each other, and the black and the green lines are close to each other. And the black and the green have the same scattering length. So this shows us that this parameter is dependent just on the scattering length and not on the absorption length. And similarly, the intensity decay is dependent only on the absorption length and not on the scattering length. And so we're hopeful to replicate this in an experiment and be able to directly measure the optical properties of those liquids. So this was the matching of our experiment and simulated data, just to show that our model is doing a good job. So the data points are the experimental data, and then the shading behind is our simulated model that we would then use to develop like a training data set for a machine learning algorithm. So, achieved good agreement here and gave us confidence that our optical parameters are pretty close to correct. So the energy resolution that we measured, we found to be relatively independent of position in the detector. So that's what we're showing on the right here. So in order to measure this, I should say we again used the laser. We injected a known number of photons and then observed how the amount of signal varied over repeated pulses, and that gives us an indication of how accurately we can measure the number of photons that were created in the detector. And we found that it obeys a Gaussian relationship. And obviously, the more photons you inject, the better the statistics of detection, and the better the energy resolution. So for small pulses of 10,000 photons per pulse, we had about a 49% energy resolution, and for large pulses, it was about 30%. So we expect that as we improve light collection efficiency, we'll continue to improve our energy resolution as well. But as I mentioned, we did find that the energy resolution was fairly independent of position in the detector, which was positive. Okay, on to kind of the most important thing here, the reason that we're doing all this topological reconstruction. So the first method that we employed to do topological reconstruction was just a simple center of mass approach. So if you look at the side of the detector, you have kind of an image of, you can think of it as like 16 pixels of these fibers coming out. So if we're considering the XZ plane right here, we can calculate the center of mass of an event in the X direction by considering the response of all the fibers that are orthogonal to the X direction. And there are 16 of them. And then similarly in the YZ plane, which would be sort of the other one over here, we again can use 16 fibers to inform the topological reconstruction via the center of mass method in the Y direction. And then for the Z direction, all of the fibers are orthogonal. And so we can use all 32. And so because of that, we have twice as much information in the Z direction as we do in the X and the Y direction. And we expect our performance to be better for that reason at reconstructing event topology in the Z direction. So one thing we found through simulation was that if you calculate the center of mass, that doesn't directly correspond to the true location of the event. There's sort of a mapping of those quantities that we achieved through, as I said, examination of our simulated data. So over here, you have the X and the Y planes. They're the same as each other because the detector is symmetrical in those dimensions. And you can see on the Y-axis here, we have the true position of events. So each one of these data points represents a separate event. So the true position of the events, and then where the center of mass value solved for. So you can see that there's in red sort of this region where the center of mass values and the true positions are roughly the same. They require some adjustment, but not much. And then there is a region of the detector where you don't get a unique center of mass value for a change in the true position. And those are the positions that are outside, sort of the most outside fibers. So we found that, fairly intuitively, you can't reconstruct positions that are outside the last set of fibers using a center of mass method. And then similarly in the Z direction, you can see that the distribution is tighter as we expect because there's more information. And also there's an offset that's related to the fact that all the photons from the fiber are pointed straight down, both in experiment and simulation. So they move on average about one mean free path before interacting and creating a light bulb. So we then use this mapping that we created to convert center of mass values to the true positions. So here in the upper left, you can see distributions of reconstructed event positions in X, Y, and Z. And then on the right, sort of a total position reconstruction error for those events. So here, this is for events that are close to the center of the detector that were large. So we have an uncertainty or a position reconstruction error of a little less than 4 millimeters on average. But if you consider the average across 4 positions in the detector at various distances from the center, for large pulses of 20,000 photons per pulse, which corresponds to about 1.5 MeV, we have a position reconstruction error of 4.4 millimeters. To put that in perspective, if you wanted to achieve that level of position reconstruction precision using a physically segmented detector, you would need about 300 voxels, each individually instrumented, to fill a volume of the same size as our fiducial volume. So because we're using 32 channels, we have a savings of about an order of magnitude of the number of channels required to achieve that level of position reconstruction precision. So you might be thinking that machine learning is well suited to this task, and it certainly is. We've just started going down the path of using machine learning algorithms to do the event topological reconstruction. Obviously, one of the most difficult things is to generate a good training data set, which we feel confident that we can do now that we have a validated simulation. But there are a lot of problems associated with trying to develop an unbiased training data set. So we're still solving some of those problems, but the initial indications are positive. This is a collaboration with Penn State University, I should say. This is the work of Garrett Wendell and Doug Cowan. And initial indications are that the machine learning algorithm outperforms the center of mass method modestly, but we're hopeful that we can continue to sort of tune more performance out of this machine learning algorithm and continue to improve the reconstruction performance. Okay, so in conclusion, sort of some of the major results that we have achieved are demonstration of the stochastic light confinement in inert opaque liquids. We've developed a model that well predicts the response of our detector for exposure to gamma rays. And then we've quantified both the energy resolution and the position reconstruction resolution of our first prototype opaque scintillation detector. There are a lot of things to do in the future. This is a very new technology. I think the first paper about opaque scintillators came out in 2021. So there's really not a lot of work that's been done yet on opaque scintillators. It's a sort of a, there's a lot of low-hanging fruit, so to speak. But one of the first things we want to investigate is a way of directly measuring the optical properties of these opaque liquids, which again is not trivial to do, but we think we have a method in diffuse reflectance that will probably work. And then once we have a really good understanding of the optical properties of some of these liquids, we then want to create a new prototype that has geometry that is optimized for that set of optical parameters to see if we can improve upon the energy resolution and the position resolution of that second generation detector. There are a lot of things to consider in materials. So plastic scintillators, for instance, can be made opaque, as you see in this image here. This was made by Colton Graham at Oak Ridge National Lab. And so opaque plastics are certainly an interesting avenue that we would like to consider. Once you relieve the need for scintillators to be transparent, it introduces the possibility of doping those scintillators with any number of compounds, exotic materials to encourage specific interaction pathways. So there are a lot of things to investigate with doping and novel materials. And then lastly, applications. So we think that this technology would be appropriate for application in muon scattering tomography. So up on just above there, you see an image of an event that we captured kind of by accident of a muon in our detector. And you can see that because muons deposit so much energy and create so much light, it's pretty easy to see even by eye what the path of that muon likely was through the detector. So we think that we could potentially improve upon existing muon scattering tomography detectors and provide better position resolution for better tomographic resolution. Dual particle imaging is something that we're interested in investigating. So far in this talk, I've just focused on gamma rays, but a detector of this style should also be sensitive to fast neutrons. And so by developing a larger detector in which there would be multiple scatters of gammas and neutrons, we should be able to, or I should say multiple interactions of gammas and neutrons, we should be able to develop a single volume detector that can provide imaging for sources of neutrons and gamma rays. Obviously, there's a lot of work to do there, but we're optimistic. And then lastly, particle type identification. I kind of touched on it on the beginning, but we think that this technology could be appropriate for discriminating between both neutrons and gamma rays using traditional pulse shape discrimination, and then also using the event topology to distinguish other types of particles. So with that, I will conclude, and I'm happy to take any questions that you might have.
Great. Nice talk, Andrew. As we wait for like questions coming through the Q&A, I already see one that could propose to you. So you have one question here. It says, is there a correlation between the photon's energy and the length of the WLS fiber in the case of an opaque scintillator?
Yeah, that's a good question. I think there certainly is a relationship between. So I'm assuming you mean the incident gamma ray. If that's not what you mean, correct me, but I think that's what you mean. So um, you would want to design a detector of proportions that were sufficient to, to allow gamma rays to interact within the volume most of the time. Um, so I think that's what you're asking. Or if I didn't understand that correctly, please try to rephrase it or let me know. Where are we at with muon detection technology? So muons are actually really easy to detect because they're charged particles and they're very energetic. So they in scintillators they produce like an enormous amount of light, which makes them sort of like one of the easiest particles to detect. Actually, so usually in most laboratory settings, they're a problem because you kind of get them muddying up your data set when you generally don't want them. So right now, I think one of the images that I showed at the beginning was an example of a muon panel. So I'll go back to it. It was one of the traditional simple. Yeah. So this thing here in the upper left, this big plastic panel, is one of the ways that they detect muons. So this is useful both to reject them from experiments where you don't want your data set contaminated with muons, and then also to do things like muon scattering tomography, where you put a detector above and below an object, and if you know sort of like the direction of the muon at the top and then the direction of the muon at the bottom, you can tell how much it deviated from its original path. And then that tells you information about what it passed through in between. So you can image things that way. What kind of calculations and data is tough to interpret because of the relativistic energies? Oh yeah, so that's certainly something that happens with muons. Uh, this isn't my area of expertise, but I'm pretty sure that the fact that muons make it to the ground is a demonstration of relativity because they're created in the upper atmosphere, and they if you don't consider relativity, they would decay, I think, before they make it to the ground. But from the purposes of, or from the perspective of radiation detection, um, we think of them as being sort of an instantaneous event. I'm not aware of any attempts to sort of uh, capture like their rate of progress through a detector. They really appear to us kind of uh, like this picture in the upper left here, where it's just you get sort of like a almost like a lightsaber passing through your detector. Like you get just a big ray of scintillation light. So I don't know if that answers your question, but I I know that there has been work done in investigating like the lifetimes of muons and what that means for demonstrations of relativity. And I think it is one of the sort of the commonly given examples of like this is evidence that relativity is real.
Cool. And I guess while we wait like one more minute to see if anyone else has any questions, I guess I can ask one in the meantime. So one thing I've been curious about is relating to your opaque simulators when you're actually producing them. Like how homogeneous are they actually within like a batch, and then how similar are they between batches if you make, say, the same type or you're attempting to make the same composition, is it actually consistent across different attempts?
Yeah, that's a great question. So I think it actually kind of ties in with one of the anonymous questions there in the chat, which is basically like how homogeneous was the milk. And so this is definitely an issue. So there are a bunch of reasons why this is an issue. For one, I think I have a backup slide here of I didn't mention it, but the opaque water-based liquid scintillator isn't perfectly stable, so it kind of like separates Yeah, so here's an image of the OWBLS kind of separating over time, which is a huge problem because in all of our modeling, we're assuming that the scintillation liquid is homogeneous in the detector and that the behavior is going to be the same everywhere. Similarly, with like the milk that we were using, we had to assume that as we diluted it further, the sort of the size of the fat molecules were staying constant, which is an assumption that may not be warranted. And similarly with the wax-based liquid scintillator, you can see the granularity of it, so you can kind of see that it's not perfectly homogeneous. And so all of those are definitely real concerns, and they certainly are going to affect the light transport, at least on a microscopic level. And it's something that as we continue to refine these liquids, have to be well characterized and well understood. I don't know if that was a satisfying answer, but it's basically the theme is it's definitely a thing that we're worried about, and we're working to understand it better.
Oh yeah, for
It
sure.
seemed
Cool.
that
Thanks.
So I got a question that says, it seemed that opaque sensors were having significant characteristic loss. Can you please clarify? Yeah, so this is a great question. So like basically what are we doing about all these sources of loss? Um, and so this is kind of an interesting thing to think about because some of them can be improved and some of them like can't be improved. Some of them are sort of, um, can't really be avoided. So the number, like this number 70% here, can be improved because if you had a scintillator with an infinite absorption length, so that the photons would just continue to bounce around until they made it to a fiber, then that number would be like 100%. So by increasing the absorption length of the bulk liquids, you can improve that number. This 80%, I think it's fair to say, is just a chemical engineering problem, just a chemical engineering problem. As not a chemical engineer, I can be dismissive of that and say that that should be a thing that we can improve, because this isn't like a physics limit. So as these fibers continue to improve in their design and manufacture, that should be something that we can improve. This one is the big problem. So this is a physics limit because it basically is a result of the different index of refraction of the fiber and the bulk liquid, and the cladding actually around the fiber. And so for those of you who have taken like an introductory physics class and are familiar with Snell's law, there is some critical angle after which refraction does not occur and all the light is reflected, and that's kind of what we're coming up against here. So there actually are some interesting and novel ways to improve this that are kind of outside the box, and I don't mean to be to be opaque about it, no pun intended. But there's sort of ongoing things that I can't talk about because they're in commercial development with Cure. But we are looking at ways to improve this number. But it's hard to do, I'll say. This one should be able to be improved in the same way as this 80%, just by improving the manufacture of the fibers. And this is something that is an ongoing area of research, is 25%, for not just opaque scintillators, but for anybody who cares about detecting photons. It's something that is an active area of research. So one way to immediately double that number is to go from using photomultiplier tubes to SIPMs, which in our next generation of prototype we're going to do. So we anticipate just immediately getting up to around a 50% quantum efficiency. And there's work being done in Canada to further improve the quantum efficiency of SIPMs up to 80 or 90%. So most of these numbers can be improved, but some of them are more difficult. Are there actually advantages of quick scintillators, or are we just trying to make them workable when a transparent scintillator is not practical? Yeah, so obviously there are like a host of problems associated with using opaque scintillators. The thing that they are great at is scalability and efficiency of channel employment when you need event topology. So if you need a large detector, like I didn't really mention it, but the group Liquido is building a multi-ton scale opaque scintillator detector that they're going to place next to a nuclear reactor in France. And so the position resolution that they're going to be able to achieve in that detector is on the scale of what I presented today. And so you can imagine trying to produce a segment detector of those dimensions, like multiple meters in length and diameter, with tiny little voxels. So it becomes rapidly untenable to segment a detector in that way when it needs to be made very large. Whereas opaque scintillators, because they're sort of natively segmenting or virtually segmenting, that can be done much more feasibly. So that's one of the advantages. Could you please expand more on novel applications of scintillation? Sure. So scintillation writ large is obviously like a huge field. There are one of the coolest light sensitive detectors that I know about is Ice Cube, which is a kilometer by a kilometer by a kilometer in the South Pole. So they basically took a giant chunk of ice and instrumented it and turned it into a radiation detector by putting photomultiplier tubes at various locations in this big chunk of ice. And they're able to image particle interactions in that ice using the ice as the medium itself, which technically isn't scintillation; it's a Cherenkov detector, but same idea. So I mentioned that one to say that there are like a ton of applications potentially for detectors of this type. Opaque scintillators, particularly, I think are potentially well suited to any application in which you care about event topology. I can't really think of an application for an opaque scintillator where event topology is not an objective. I think in that case you'd be much more well suited with a traditional scintillator. But anytime you care about event topology for whatever reason, be it background rejection or pileup reduction or particle type identification or any of those things, we've solved those problems in other ways in the past, but I think it bears investigation whether opaque scintillators would be appropriate for some of those applications. Hopefully that answers your question.
Cool. And all right. And I think with that, we are at time. So thank you, Andrew, again for the great talk. And then thanks everyone else for listening. And hope to see you guys next for the future lectures in the summer school.
Thanks everyone for your attention. If you want to follow up with me, my email address is there on screen.
All right. Take care, everyone. Bye.